Hello there. So today I will show you how to balance any redox reaction in both basic and acidic solution. So the strategy for any specific redox reaction is the same, and for both types of solution, this strategy is identical up until the very end, where there is an additional step if we're in basic solution. Okay, and I will of course show you that. So either way, to get started, we need to break down this redox reaction into its reduction and oxidation half reactions, okay? And in order to do that, we need to figure out which element is getting reduced and which element is getting oxidized. And in order to do that, the best thing we can do is label the oxidation states for every single element across the entire reaction, okay? So, to get started, I will go always left to right. We have permanganate. So as we know, oxygen here is going to be -2. The exceptions are any kind of peroxide, right? Hydrogen peroxide, sodium peroxide, where oxygen is -1, right? And that's because the counter elements here, sodium or hydrogen, they can only be +1, right? So there is no possible way for oxygen to greed more than just 1 electron per oxygen atom. Okay. And you may see something with a fluorine. This is a little rare. Any oxygen fluorine bond, the oxygen will actually be positive and the fluorine will be negative to some extent, depending on how many fluorines there are and so on. And that is because fluorine is the most electronegative element, right? The only element more electronegative than oxygen. So it actually takes those electrons from oxygen, so to speak. It is still a covalent bond, though. And you may see something like elemental oxygen, right? 0, because there's an equal sharing. And you may see something this is more rare, a superoxide, right? So this is called a superoxide ion. It's O2 minus, so each oxygen is actually -1/2. So these are all the possible exceptions you could need to know about, but the main one is just peroxide, hydrogen peroxide, where oxygen is -1, not -2. Okay, clean that up. So oxygen here is -2. Great. There are 4 of them. So I multiply this -2 by 4. We get -8. And that regards this O4 unit, okay? So always the summation of every oxidation state of every element in a compound or ion, whatever it is, always equals the overall charge here, right? So here we have a -1 charge. And if the summation, the sum of all the oxidation states for all these elements must be -1, and oxygen contributes -8, manganese here must be +7, right? 7 minus 8, -1. So there we go. Moving to the right, iodide, pretty easy, must be -1 because it's overall -1 and it's the only element there. On the product side, we have manganese dioxide. So oxygen here, again, -2 because it's not an exception. So we multiply that by 2 for the 2 oxygens present. Overall, we have -4 from the oxygens. The overall charge is 0, right? This is not an ion. So this is the more simple case where we just need the same amount in the opposite sign, right, to equal 0. 4 minus 4 is 0. So we know manganese there is +4. And iodine, gas, of course, elemental, so it's 0. Okay, so now we have labeled the oxidation states for every element, right? In the whole reaction. And we have a clear story of what happened, right? So manganese went from +7 to +4. That's a reduction of 3 electrons, right? And iodine went from -1 to 0, so it lost 1 electron. Okay, so now we know what elements to use for our half reactions. First, I will do the reduction half. Okay, so when you're breaking down your half reactions, or you're breaking down the full reaction into your half reactions, you always just include whatever compounds or standalone elements, whatever it is, have your elements of interest, right? So everything that has manganese on the left from the full reaction goes on the left for my reduction half reaction, okay? So I will put down my permanganate, and everything on the right from the full redox with manganese goes on the right here. So that would just be MnO2, okay? There are a few different ways to go about this. The steps are the same, but the order you can kind of choose, right? So we have to balance the elements, and we have to balance the charge, okay? So you could start playing with electrons first or elements first. I always like to do it elements first. I always balance my elements first. So we have 1 manganese on the left, 1 on the right, so manganese is balanced. We have 2 oxygens on the right and 2 on the left. Okay, so to balance oxygen, we always use water, okay? Because we are in an aqueous solution. Okay, so now I have 4 oxygens on the right, 4 on the left, great. But I've introduced 4 hydrogen, right? So now I need to balance that with 4 protons on the left. This is true for acidic and basic solution, right? You will use protons, okay? Again, the processes are the exact same for basic and acidic up until the very end. And I will make that very clear when we're at the very end. So, great. You balance your central element first, right? Manganese in this case, then oxygen with water, and then hydrogens with protons, okay? So now our elements are balanced, right? We have 1 manganese, 4 oxygens, and 4 hydrogens on both sides, but the charge is not balanced, okay? So on the right here, we have an overall charge of 0, and on the left, we have an overall charge of +3. That is an obvious issue, okay? But this is a very expected discrepancy, right? Because this is a reduction half reaction. Reduction means that we are gaining electrons, or we are putting in electrons on the left side of the reaction, right? And as we knew from up top, manganese went from +7 +4, it gained 3 electrons, and that obviously cancels out the charge discrepancy, right? So when we incorporate our 3 electrons, again, 1 electron is worth -1. So now this goes to 0, and the elements and the charge are balanced, and so the entire reaction, the half reaction here, is completely balanced, okay? Clean this up. Great. Now for the oxidation half. Obviously, we're working with iodine. I'm going to scroll down a bit. Okay. So iodide on the left, turning into iodine gas on the right. Iodine is not balanced, so we will quickly balance that. Easy enough, 2 iodines on each side. Now the charge is imbalanced, right? The left side is overall -2, and this is still just 0. And again, we know this is an oxidation reaction, so we are putting electrons on the product side, or we are losing electrons, right? Well, in this case, instead of canceling out a positive charge to balance the charge of the reaction, I am introducing negative charge on the opposite side. So now each side is -2, okay? And so now this is a fully balanced oxidation half reaction, okay? So we're making some good headway here. Once we have these balanced half reactions, you might think, okay, great, now we add them together, right? True. But we have to consider the number of electrons being transferred. Okay, so a redox reaction is like a handoff of electrons, right? I give 3 electrons over to you, right? I was oxidized by 3 and you were reduced by 3. So there is this shared number of electrons that must be equal on the right side of the oxidation half and on the left side of the reduction half, right? Because whatever electrons I'm giving up from my oxidation reaction are the electrons that we see over here in the reduction half, right? And vice versa. But you may have the grace of having a very simple reduction or a redox reaction where it's just 1 electron each or 2 each or whatever, and you don't have to do anything extra. But in this case, we see that there is a discrepancy, right? I'm giving away 2 and I'm receiving 3. Okay, if you have this kind of scenario, you always find the least common multiple for your number of electrons on your oxidation and reduction halves, okay? So the least common multiple is just the smallest whole number that both of your numbers can go into, right? Evenly, let's say. Bit of a refresher there. So the least common multiple of 2 and 3 is 6, right? Okay. With that knowledge, we need to make the electrons equal 6, right, for both of these half reactions. And in order to do that, we actually have to balance, or rather multiply, each entire half reaction by the necessary number, right? So for the reduction half, we want to get 3 up to 6, so we just multiply it by 2, but we need to multiply the entire reaction by 2, right? Everything gets multiplied by 2. Same idea down here. Everything gets multiplied by 3 to get up to 6, okay? So now I will just rewrite it down here, right? We now have 6 electrons plus 2 permanganate and 8 protons going into 2 MnO2 and 4 water. In our oxidation half, we have 6I minus going into 3I2 and 6 electrons, of course. Okay. So just clean this up a bit. All right. So now we have truly fully usable half reactions, right? As a side note, I'll go actually again. As a side note, with the LCM stuff, that means you're always going to be raising a number like 1 up to the other number, right? So that's a little vague. So if you have, let's say instead of 3 and 2 electrons, right, I had 3 and 1. So obviously one way to balance this is to divide the reduction half by 3, right? Don't do that, okay? If you have 3 and 1, just multiply the oxidation side by 1 and do nothing to the reduction half, okay? So that's just, again, reiterating, you always use the least common multiple or the smallest whole number that both numbers can go into evenly, right? Okay. So now we're working with our 2 fully balanced, fully usable half reactions, okay? Now we can add them. In fact, we can, before we even start adding them together, we can start canceling things out. So a general rule in chemistry always, right, is when you have the same thing on the left as on the right, even if it's across, right, even if it's across 2 reactions, we're going to be adding these together, making 1 reaction. You can cancel them out, right? So I see, okay, great, I have 6 electrons here. I can cancel them out here too. That is all that I can cancel for now, right? So then the full reaction, again, I would combine the products and combine the reactants. So it doesn't really matter the order, right? So 6I minus plus 2MnO4 minus plus 8H plus goes to 2MnO2 plus 4H2O plus 3I2. So this is your fully balanced, completed acidic solution oxidation reduction reaction, okay? If you were that is to say, if you were being asked to balance this in acidic solution, this is how you would leave it, and you would get 100% on that question, okay? But if you're in a basic solution, I mentioned that extra first step, okay? So again, this is for acidic. Now, what if we're in basic? Okay, I don't know why it's selecting that too, but we'll just ignore it. Okay. So the extra step is simply to add hydroxide ions to neutralize any protons to create water. And those water molecules will then cancel out probably with other water that is already present. All right. So again, I'll rewrite the whole thing. Okay. Okay. So as I said, if we're in basic, we add 8 hydroxide ions to neutralize the 8 protons. But when doing this, we have to do it to both sides. So we also need to add 8 hydroxide ions to the right. Keep things even, okay? So simply, right, these will become 8 water, right? So I will just replace it with 8H2O. But we already have water on the right over here, right? And as I've mentioned, and as you know, things that are shared on the left and right can be canceled. So in this case, we actually just get rid of all of the water, and we reduce this by the amount we canceled by 4, right? So now we just have 4H2O on the left. So cleaning this up a bit, right, we would rewrite this as 6I minus plus 2MnO4 minus plus 4H2O. Okay. So now this is a fully balanced reaction in basic solution. So that is the only difference, right? You add the hydroxides to both sides, neutralizing the protons into water. Then you'll cancel out some of the water, right? Because there's already water present on the product side. And then you just rewrite it for cleanliness, and that is it. Okay, thank you for watching, and good luck.